Welcome to the isomorphisms lesson from the series The Shape of Space Linear Algebra. I kind of hinted at this a few times before, and we've proven some theorems about the dimension of a vector space. Now we're going to, in this lesson, show that for a given dimension, a finite dimension, all vector spaces are what's called isomorphic. They're the same in terms of their vector space properties. I just have a few examples here that we've talked about before. We have the set of matrices of size m by n, and we know that we can get a basis for this just by putting a 1 in one spot and a 0 in the other entries, and doing that for each of the possible spots or locations in our matrix, and we get a basis of size m times n, and that's isomorphic to the Euclidean space of dimension mn, and then that in turn is isomorphic to the set of polynomials over the real numbers of size mn minus 1, and I just wrote it out here just because you may be curious why there's a minus 1 here. It's because you start with the constant, and then the coefficients go from a sub 0 all the way up to a sub nn minus 1. So the dimension is actually mn. In this lesson, we'll talk more formally about isomorphisms. We'll first define what it is, and then we'll prove a few theorems related to that. So I'm repeating myself a bit here in the first paragraph, but just to emphasize the point, we've seen some examples that appear to be essentially the same in terms of vector space properties, but have differences with respect to other properties, which I mentioned. So for example, a four-dimensional Euclidean space and the set of all 2x2 real matrices are isomorphic. Each is of dimension 4. Addition is on a component-wise basis, and scalar multiplication applies across each component. When I say component, I mean either the component of R4 or the entry in the 2x2 matrix. So let's look at a formal definition here, and I'll get into these terms in the next slide if you haven't seen them before. So two vector spaces, V and W, are said to be isomorphic. We write it like this. If there exists a mapping from V to W such that the following hold true. F is 1 to 1 and onto, which is sometimes known as surjective. 1 to 1 is sometimes known as injective. And if you have both of these properties as a function, then you're classified as being bijective. And then you have these other two properties here. F of V1 plus V2 equals F of V1 plus F of V2 for any two vectors in V. And then if you have f of AV, where A is a scalar, that equals A times f of V. And you can combine these two properties. It's basically saying if you have a linear combination of two elements from your domain, then you can break it up into a linear combination of the elements after they're mapped into your codomain W here. So this is equivalent to these two together. Let's review what's meant by injection, or 1 to 1, surjection, or onto, and bijection, which is 1 to 1 and onto. I took these diagrams from the Wikipedia article, and the thing to note here is the domain and codomain are just finite sets, but I think it still illustrates the point. So let's start here on the upper left. We have an injection, but it's not surjective. So each element of X is mapped to one element of Y, and it's an injection for that reason, but the element C in Y has nothing mapped to it from X, so that means it's not a surjection or onto. So this is an example of an injection that's not a bijection. And the mechanism for proving that something's an injection is one of two ways. You can either take f of x1 equals f of x2 for any two elements in your domain and prove that x1 must equal x2, or you could do it by contradiction. You could take two elements in your domain that are unequal and show that that implies that the mapping under the function is not equal. In the second example, we have onto or surjective, but not injection. You can see it's onto because every element in Y has something from X mapped to it. It's not an injection because you have 3 not equal to 4 using this condition down here. 3 not equal to 4, however, f of 3 does equal f of 4, so it doesn't fulfill this implication here, so it's not an injection. And then in the third example, we have both properties. You notice for every element of x, there's a map to an element of y, and then every element of y has something from x mapped to it. So it's kind of what you would think in the finite case. You have a one-to-one and onto mapping here. Then just to remind you, a function from a set x to a set y assigns to each element of x exactly one element of y. So everything here is a function. If I, for example, mapped 3 to a and b, then you wouldn't have a function because it would violate the definition here. And then finally, the Wikipedia article gives an example of something that's neither injective or bijective. So it's not injective because you have two elements mapped to the same element in y. It's still a function, but it's not injective. And then it's not surjective or onto because there's an element a here and it has no element of x that's mapped to it. So we violated both conditions here. Okay, so normally in our discussion with isomorphisms at least, we're looking to have bijection, which has, and the other property about mapping a linear combination in the domain to a linear combination in the codomain. Let's return to our example from earlier and actually prove that R4 and M2 by 2 are isomorphic. We'll define it this way here, where if we take V, these components from R4, then f of V is just this matrix here. First step is to show f is injective, and as we know from the previous slide, there's two ways of doing that. We can show U does not equal V implies f applied to V does not equal f applied to U, or we can go in the other direction and show that if the functions are equal, the function is equal, I should say, at the two different values U and V, then U has to equal V. So we'll take the latter approach. So assume that we have U and V from R4 and the function evaluated at these two vectors are equal. So that means using our definition here, we have this being equal. But by the definition of matrix equality, V1 equals U1, V2 equals U2, V3 equals U3, and V4 equals U4. In other words, V equals U. So the two vectors are the same. So that proves one-to-one. Showing that f is onto or surjective is even easier, since every element in our set M22, every element in this form here, where these are real numbers, has a corresponding element from R4 mapped to it. So that's pretty obvious. You just pull these out and put them into a vector, and that tells you what gets mapped to it. So that gives us surjective. So we have injective and surjective. In other words, the mapping is bijective. And then we just need to prove the linearity property. We take f of a linear combination, AU plus BV, where we defined U and V as we have here. And then you add these together, and then you just put the components in the appropriate positions, as I've done here. And then you break them into two pieces. Right, this sum here equals this matrix. And then, of course, this is A times F evaluated at U and B times F evaluated at V. So that proves the linearity property. And so we've proven that R4 is isomorphic to the set of 2 by 2 matrices under this mapping here. As an exercise, you may want to show that the set of real polynomials of degree 2 or less, in other words, this set here, is isomorphic to R3. It's pretty easy to show, but it'll at least force you to exercise your understanding of the definition of isomorphism. And then we have one additional definition. An isomorphism between a vector space and itself is known as an automorphism. And I have an example of that here. So the vector space R is automorphic to R under the mapping f of x equals cx, where c is a constant. We have a couple of theorems concerning isomorphisms on this slide. First one is an isomorphism maps the zero vector of one vector space to the zero vector of the other vector space. So let F be an isomorphism between vector spaces V and W. For any V in our vector space V, we have the following string of equality. So we have F of the zero vector in V, and that would equal 0 times any vector V. We proved that earlier. And then by the linearity property, we can bring the 0 out here. But now we have 0 times f of v. But f of v is an element of w. And so 0 times any element of w is the 0 vector of w. And that's what we wanted to prove. The second theorem is the inverse of an isomorphism is also an isomorphism. We have from basic function theory that the inverse of a bijective function is also bijective, so we have that. But what we want to show also is the linearity property. So we want to show that f of a w sub 1 plus b w sub 2 equals a times f inverse of f w sub 1 plus b times f inverse of w sub 2. And that's fairly easy to show. So we just to set this up, F is an isomorphism from V to W, and if we take W1, W2 from W, where F of V sub 1 equals W1 and F of V sub 2 equals W2. So that's setting up what we want to show here. So we take the inverse, F inverse of AW sub 1 plus BW sub 2, and then from the linearity property and what we've stated up here, this is the same as this. We've just substituted in here and here for these two. And then I should have said from the linearity property we go to this step here, because this is equal to this from the linearity property. So I misspoke on the initial step here. And then F inverse of F is just the argument of this in here, so that gives us A V1 plus B V2. And then V1 is equal to, if you just take the F inverse on both sides of this, it equals F inverse of W sub 1, and the same thing here. And that's what we wanted to prove. So the inverse of a isomorphism is also an isomorphism. Before we get to our main theorem, we need to introduce the idea of an equivalence relation. So let's do that. An equivalence relation R is a binary relation on members of a set X, and that fulfills these three properties here. Reflexive. So for every element in S, A is related to itself. Then symmetric means if A is related to B, B is related to A. Intransitive is A is related to B and B is related to C, then that implies A is related to C. So the important thing is that if you have an equivalence relationship, your set is divided into what are called equivalence classes. A common example is the integers modulo n. So for example, if we take the integers modulo 7, that partitions the integers into 7 equivalence classes, one class for each remainder when an integer is divided by 7. And we write it like this for the equivalence class. So this is the one for 6. So it's everything, all the integers that leave a remainder, a positive remainder of 6 when you divide by 7. So for example, 20, if you divide that by 7, it equals 2 times 7 plus 6. And if you have minus 15, that's a little bit tricky. You have to have a positive remainder there. So it's really minus 3 times 7, which is minus 21, plus 6, and that gives you minus 15. So you may want to just try another one, like, say, the equivalence class for 3 or 4, and see, just to convince yourself that you understand this idea. Okay, so now what we're going to do is apply that principle to isomorphisms in the theorem on the following slide. The following theorem establishes that the relationship isomorphism is an equivalence relation among vector spaces. So we have to show reflexive, symmetric, and transitivity. So in terms of the reflexive property, every vector space is isomorphic to itself. We can prove that fairly simply. Take the identity mapping from V to V, where every vector V in our vector space V gets mapped to itself. This upside down A means for every. So clearly the identity mapping is bijective, and it also has the linearity property, because the identity mapping of AV plus BU, where A and B are scalars, is just mapped to itself, and then V is the same as the identity mapping of V, and B and U is the same as the identity mapping of U, and so we have the linearity property here. Then in terms of the symmetric property, we already proved that in theorem 27. If you have an isomorphism F between vector space V and W, then F inverse is an isomorphism from W to V. And as I say, that was theorem 27. We proved that a few slides ago. In terms of transitivity, assume F is an isomorphism from V to W, and G is an isomorphism from W to X. Then we take the composition of G with F, in other words, G of F. That'll go from V to X. And we have a couple of things to prove here, but one we already have from function theory. The bijection of a bijection, in other words, the composition of bijections is again a bijection. So we know that we have a G of F is a bijection from V to X, and then we need to show the linearity property. So we have G of F, and that we take a linear combination of the space we're starting from V, and then this is just the definition of G of F. It's G evaluated at F, where F is evaluated at this particular point. And then we expand this out because we know F is, by assumption, is a isomorphism, so we can write it like this. And then we know that G is an isomorphism, so we can bring out the A here And then g of f of v1 is just by definition g of f, and g of f of v2 is g of f of v2 by definition. And so we have the transitive property. We have the g of f is a isomorphism between v and x, where we started with v being isomorphic to w and w being isomorphic to x. So a bit long-winded, but we've shown that isomorphism as a relationship is an equivalence relationship between vector spaces. We're going to show that isomorphic finite dimensional vector spaces have the same dimension. And the approach here is to demonstrate a mapping between the bases of two isomorphic vector spaces, which we'll call v and w, and then we can conclude that they both have the same dimension. So let f be an isomorphism from v to w, and let S be the basis for v, so implying v is of dimension n. The image of S in w is the set T, f of evaluated at each one of these vectors. We want to show that T is a basis for w, and then we can conclude that w is also of dimension n, which would prove our theorem. So we have two things to prove. First, that we have a spanning set, and then that we have linear independence. So take any vector w in our vector space, capital W. Since f is an isomorphism, it is an onto mapping, and so there exists a v, vector v, in a vector space v, such that f of v equals w. We can write v in terms of the basis S. So we have w equals f of v, and then writing v is a linear combination of the basis vectors, and then we can expand that out this way using the linearity property, which works even if you have n, linear combination of n things. It's just by induction. And so any vector w in our vector space capital W can be written as a linear combination of the vectors in T. So in other words, T spans W. Next, we show linear independence. Consider a linear combination of vectors in T that's equal to the zero vector in W, this here. Then using the linearity property, we know this equals this. But we've proven earlier that F is a one-to-one mapping. If F is a one-to-one mapping, we know that it maps the zero vector, its zero vector in vector space V, to one and only one vector, the zero vector in vector space W. So in other words, this thing inside of here must be 0. But then since S is a basis for V, we know that this linear combination, all the coefficients must be 0, which in turn shows that this linear combination, if it equals 0, all the coefficients must be equal to 0. In other words, the vectors in T are linearly independent. And so that's the proof of our theorem. We could also prove this in the opposite direction, and I'll do that in the following couple of slides. Theorem 30, finite dimensional vector spaces of the same dimension are isomorphic. So this is the converse of what we proved on the previous slide. Our approach will be to show any vector space V of dimension n is isomorphic to Rn, n-dimensional Euclidean space, and then it follows by transitivity from theorem 28 that all such spaces are isomorphic to each other. So let S be a basis for an n-dimensional vector space V. Define a mapping from V to Rn, n-dimensional Euclidean space, using the representation function. So f of V equals a representation of V in terms of S. And if you recall, we defined this a few lectures ago. It's just a matter of writing V as a linear combination of the basis vectors and then taking the coefficients and putting them into a vector. So since V has a unique representation in terms of the vectors of our basis S, f of V is mapped to a unique element Euclidean n space. So the function is well defined. We also want to show it's one-to-one and onto, which we'll do here. F, to show F is injective or one-to-one, let V equal linear combination of the basis vectors, and U be another vector that's represented in terms of the basis vectors, and assume that that F evaluated at V and F evaluated at U is equal. Then the representation, this here implies representation of V in terms of S equals this by definition, and the representation of U with respect to S equals this here. But if these two vectors in Rn are equal to each other, then AI equals BI, for I equals 1 to n, and thus V equals this linear combination. But since each one of the AIs equals the BIs, that equals this, and that equals U. So if we have this, then it forces us to have U equals V, and that was one of the ways of proving something is one-to-one. So let's continue. We want to show onto, and of course we want to show F has a linearity property, and then we would have the isomorphism that we're looking for. Let's finish off our proof. Show that F is surjective for every W equals W1, W2, all the way up to Wn, an element of Rn. We can represent or create a vector V that uses the W1 to Wn as its coefficients as a linear combination of the basis vectors. And then by definition, V is mapped to W by our function F, and so F is surjective. Finally, we need to show linearity. So if we let U, V and U were defined in the previous slide, which I've copied here, what we want to show is that F of xv plus yu, where x and y are scalars, equals this expression here, and that gives us the linearity. So by definition, f of xv plus yu is the representation of this vector in terms of s, and then we can plug in u, v and u here, multiply it out, and we get this, and then we just use the definition of the representation with respect to s, and we pull off the coefficients, which I've done here, and then this could be written as x times a vector comprised of the a coefficients and y times a vector comprised of the b coefficients. And you can see if you add these two together, you come back to what's here. But then this is equal to x times the representation of v with respect to s plus y times the representation of u with respect to s. And that equals x times f evaluated at v plus y times f evaluated at u. And that gives us our linearity property. So we've shown all the criteria for f to be an isomorphism, and thus every n-dimensional space is isomorphic to Rn. And we can summarize the last two theorems in one theorem. Each finite dimensional vector space is isomorphic to one and only one of Rn. And another way of expressing this is to say that every vector space of dimension n is isomorphic to Rn. Okay, so that's the last slide in this lesson. I want to talk about homomorphisms in the next lesson. That's sort of like an isomorphism, but we drop some of the criteria. So it's sort of like a lesser constraint, but it turns out a lot of more things are homomorphisms, and we end up using that concept more than isomorphism as we proceed in the series of lessons.